We're going to start this lecture now. My name is Ken Herwig, and I'm here at Oak Ridge National Laboratory, and I work in the Neutron Instrument and Source Division, and I've been using neutron scattering in my own scientific program now for a long time, and I've built several instruments at various facilities, both reactors and spallation sources, and I'm very pleased to be asked to give this lecture on one of my favorite neutron scattering techniques, quasi-elastic neutron scattering, and this is the 11th lecture in the Neutrons and Soft Matter Cyber Series, and very much looking forward to telling you about this technique and getting some of your feedback as we go. We will stop about halfway through the lecture to take some specific questions. It's kind of a pausing point as we finish the general introduction and some overviews of instruments and instrument types before I go into a couple of specific examples. But if you do have any questions along the way, please type them into the chat box and I'll take a look at them. Hopefully it'll catch the corner of my eye, and I'll try to answer them, or if they're going to be coming up in the next slide, we'll just pick them up at that point. So let's begin our lecture. We'll start with the outline. I'm going to give a little bit of a background on the difference between coherent and incoherent neutron scattering and their origins. In particular, I think the last several lectures on neutron scattering have focused primarily on coherent scattering techniques. And in coherent scattering techniques, you're looking at correlations that arise between particles. Often the incoherent cross-section, which is a single particle scattering event, is treated primarily as background. And so for Bill Hamilton's lectures on reflectometry and SANS, the incoherent scattering cross-section of hydrogen is really an annoying background, something that he has to learn to live with. But for us, it's going to contain a lot of very interesting information on the dynamics of the particles that are in our sample. I'll talk a little bit about neutrons and quasi-elastic scattering as an overview. We'll go through one representative experiment design. We'll look at what would sample thickness and quantities look like for water. I'll give you the connection to molecular dynamics simulations. We'll talk about the elastic incoherent structure factor, which is a concept you'll see in the literature on quasi-elastic scattering. The role of instrumentation is quite strong in designing both an experiment and in the information you want to extract, and so we'll spend some time looking at that. At that point, we'll pause for any specific questions that have come up during the lecture, and then we'll go through a couple of specific science examples and try to illustrate some of the information that you can extract from quasi-elastic scattering. We'll finish with some references that I like, books and articles that you can look up if you want to learn more about the technique, and we'll finish with a summary and then any final questions that you might have. So incoherent and coherent scattering. Incoherent scattering arises anytime your sample has a random variability in the scattering lengths of the elements or isotopes of the atoms that are present in your sample. And that can come up even if you have a single element sample in a couple of cases. One is if there are different isotopes of that element present, or in the case where your atom has a non-zero nuclear spin and there is a random variation in the orientation of that spin with respect to the nuclear spin of the neutron beam. In both those cases, you'll get an incoherent scattering contribution from your sample, and there's different types of information that are encoded in that signal as opposed to coherent scattering. For coherent scattering, you're getting information on spatial correlations and collective excitations in motion. For elastic coherent scattering, that is where the neutron has not exchanged any energy with the sample, it answers the fundamental questions of where are the atoms, and powder diffraction, what is the arrangement with respect to one another. For SANS, what are the shape of the objects and those types of things. Inelastic coherent scattering tells us information about collective excitation, like phonons, for example. Incoherent scattering, on the other hand, tells us information about single particles and what they're doing. And of course, the neutrons are probing the entire sample, and you're getting an ensemble average of the information. But nonetheless, it's about the behavior of single particles. Elastic incoherent scattering can give us things like the Debye-Waller factor. If you calibrated your instrument and you understand the strength of your scattering relative to a standard, you can do things like count the number of hydrogen atoms that are present in the sample. It does give us the elastic incoherent structure factor, which tells us about the geometry of the types of motion that we're probing, whether it's continuous or jump diffusion or rotations, dynamics that's restricted to a particular volume of space. Those types of things are encoded in the elastic incoherent structure factor. The inelastic incoherent scattering tells us about diffusive dynamics. Gives us things like self-diffusion coefficients and tells us how fast atoms or ions are diffusing in the materials that we're studying. So there's a very good basic discussion on all of these things in a couple of books. One which is still available, it's called The Methods of X-ray and Neutron Scattering in Polymer Science. I think you can still buy this one, and it's probably in most of your libraries. A book that's been out of print for a long time but is a classic in the field is The Theory of Thermal Neutron Scattering by Marshall and Lovesey. If you can find a copy, hold on to it and take a look at it. It's got some very nice discussions about neutron scattering in general and the difference between coherent and incoherent in particular. So for our particular scattering technique, quasi-elastic neutron scattering, the incoherent scattering from hydrogen has been a strength. Hydrogen has a very large scattering cross-section, total scattering cross-section in comparison to other elements in the periodic table. And you can see some of that down here in the red, which shows the total neutron cross-section. And in particular, its incoherent cross-section is much stronger than any of the other atoms in the periodic table and the isotopes that we're going to talk about. So it has a large incoherent neutron scattering cross-section. In our case, we're going to play the game of isotope contrast by using this relatively small scattering from deuterium to mask the contribution to our signal from parts of the samples that we're not interested in. So in our case, we're going to protonate parts of the sample that we care about and deuterate parts of the sample that we don't care about. So for example, if we were interested in the side chain motions of proteins in solution, we would protonate those parts of the protein that we care about, deuterate the solution in the buffer to hide and mask and reduce this contribution to our total scattering. The self-dynamic structure factor is, of course, what we're interested in Quens, and that is an incoherent. We do get that information from an incoherent scattering process. So why should you care about quasi-elastic neutron scattering? After all, there's a whole tool set that you have, both in neutron scattering and in other probes of soft matter. Well, first of all, it's applicable to a wide range of science areas. Biology, looking at waters of hydration and trying to understand how phase transitions, dynamic transitions occur in proteins as a function of hydration level, and what the role of water and solvation is in biology. For chemistry, you're interested in complex fluids, ionic liquids, water at interfaces and clays, water in porous materials on surfaces, those types of things. In material science, there's a lot of quasi-elastic scattering work done in hydrogen storage, looking at fuel cells, polymer side chains, proton conductors, and even lithium-ion conductors. So there's a lot of application of quasi-elastic scattering. It does probe true diffusive motions. It's looking essentially at an ensemble average across your sample of all the atoms that are present, looking at how they're moving. And so for samples in particular that contain hydrogen, you're often dominated by the scattering from the hydrogen itself. One of the things that I really like about quasi-elastic scattering is that there's a range of analytical functions that can be used to interpret and provide a framework for understanding your data. That's very useful when you're controlling your sample parametrically, like temperature or pH or other thermodynamic variables that you might be interested in looking at. the analytical models that you can use to analyze the data give you a nice framework for understanding what the systematic differences are between those measurements. There are particularly close ties to theory, molecular dynamics simulations, and I'll show you that connection later on in the talk. It is a complementary probe to other dynamic probes that you might be more familiar with, like spectroscopies, NMR, or dielectric relaxation. It's complementary. It gives you direct information about the geometries of the motions that you're studying. And that's really its strength, I think, in comparison to those techniques. So it can answer questions that you can't answer with other methods. If you look in the literature and you do a simple search on neutrons, and either quins or quasi-elastic, in either one of its two forms that I've given in the chart over here in the corner, you'll see that there's about 100 to 120 papers a year published in this field, and that's fairly typical. It's fairly constant over several years, and some of them are relatively high impact. And so you might take a look at the literature to see where quasi-elastic scattering is playing a role. So I know that you've seen lots of cartoons of neutron scattering experiments, and I'm just going to introduce a few terms here. We have the incident neutron with a wave vector Ki, a scattered neutron with wave vector Kf. The neutron goes off, hits a detector at some scattering angle, theta, and you have a q vector, a momentum transfer of Ki minus Kf. It is a vector quantity, but very often in quasi-elastic scattering, you're looking at powder samples, and so you're doing an ensemble powder average when you're actually analyzing your data. So the wave vector, of course, is just 2 pi over the neutron's wavelength. The neutron's energy is h bar squared k squared over twice the mass of the neutron. And the energy transfer is the difference essentially between the wave vectors. It's the incident energy minus the final. So a few terms over here. Q, of course, is the momentum transfer. Omega is the energy transfer. When omega equals 0, we call it elastic scattering. There's no energy transfer to or from the sample. When it's not equal to 0, we typically call it inelastic. But when it's near 0, but still inelastic, we tend to call it quasi-elastic scattering. There's actually a quasi-elastic approximation, and I'll tell you a little bit about what that means in terms of what you measure here in just a minute. So this is my cartoon to leave an image in your mind about what quasi-elastic scattering is. So I tend to think of the atoms in my sample as the billiard balls on a billiard table, and the neutrons as maybe a cue ball that comes in a particular direction. So here we have the neutrons coming in a particular well-defined direction to our sample over here. It has a wave vector Ki, a direction along here, and each one of the Ki's are essentially the same length. So it's a monochromatic beam of incident neutrons in this case. As the neutrons come into the sample and they interact with the sample atoms are moving in a variety of directions, all with different lengths of their own scattering length vector, their own K vector. And as the neutron interacts with it, they scatter off in a different direction, and we have the final wave vector shown here at 90 degrees. So in a quasi-elastic neutron scattering experiment, the neutron exchanges relatively small amounts of energy with the atoms in the sample. Harmonic motions in this approximation look like a flat background, okay? And they simply take intensity away from the elastic peak and distribute it equally across the energy transfer. Vibrations are often treated as an inelastic Debye-Waller factor for just that reason. The maximum of the intensity that you measure is always at energy transfer omega equals 0. And sometimes it's very sharply peaked there if you have a lot of elastic scattering from your sample. We do sample the component of the motion that lies along the Q vector, but as I said before, often your samples are powder, and we do an isotropic average, and we don't often care much about Q vector. The Qs that we do look at are typically less than about 5 inverse angstroms. So let's spend a little time and take a look at how you design an experiment for quasi-elastic measurement. So if sigma, little sigma, is the microscopic cross-section, it's the one that you're familiar with. It's in barns per atom, or 10 to the minus 24 centimeters squared per atom. N is the number density. It's the number of atoms in your sample per centimeter cubed. Capital sigma we'll define as the macroscopic cross-section, which is just the product of the number density times the microscopic cross-section sigma. In that case, the transmission simply depends on the sample thickness T as this exponent that I showed by here. T is the exponent of minus capital sigma, the macroscopic cross-section, times the thickness. A very good rule of thumb for a quasi-elastic experiment is that the transmission is 90%. The reason you don't want to exceed 90% or thereabouts is that then you have so much multiple scattering in your sample that the approximation that the neutron is only scattered once is no longer good. And if once the neutron is scattered more than once, it's very difficult to interpret the data. People have tried to do stronger scattering samples and then do Monte Carlo or simulations, for example, of the sample to try to extract the single scattering information. But in general, most people tend to keep their samples around 90% transmission. So the rule of thumb, if you work that out for about a 10 square centimeter sample, is that you'd like about 5 to 15 millimoles of hydrogen atoms in your beam, or the equivalent if the atoms have a smaller cross-section. 5 to 15 millimoles can sometimes be challenging. That can be a lot of sample, particularly if you're talking about a protein or something which is difficult to make. But for something like water, it's a very small amount of material, and we'll look at that here in a minute. So for typical instruments in the US that have about 9 or 10 square centimeters of sample area, like BASIS or the co-neutron chopper spectrometer at the SNS, or the high flux backscattering spectrometer and disk chopper spectrometers at NIST, this is about the rule of thumb that you'd like for a sample. So let's walk through that formula for the case of water. So water is, we'll calculate the number density first. It's 1 gram per cubic centimeter. 1 mole per 18 grams. We multiply by Avogadro's number, and you come up with a number density of 3.34 10 to the 22nd per cubic centimeter. We're going to take hydrogen as our canonical case, so we've got 2 hydrogen atoms per water molecule, and each one has 80 barns of cross-section. So sigma, the microscopic cross-section, is 160 barns for the water molecule, and we're just going to ignore the contribution from the oxygen atom. It's much smaller than that from the hydrogen. The macroscopic cross-section then is about 5.34 inverse centimeters. Right? You take that and you put it into our formula for the transmission. You take the logarithm of that to go back to the sample thickness. And so we have minus the log of 0.9 over 5.34, and we find that the ideal water sample is only 200 microns, 0.2 millimeters thick. And so that can sometimes pose a challenge in creating very, very thin samples when you have essentially entirely hydrogenous samples. We often, because for disk chopper spectrometers and for backscattering, we often prefer cylindrical geometries for our samples. So we would tend to make annular cells that consist of 2 concentric cylinders of, say, aluminum or maybe quartz, with a very, very thin annulus volume in between them, so that our total sample thickness is on the order of about 0.2 millimeters. So, as I said, that can be a challenge, but can also be an advantage if you want to look at hydrogen in the middle of something else like a solvent. So, what do Quinn spectra look like? I used to always say that small angle scattering spectra look the same. You know, they start high and they fall off low. But quasi-elastic scattering typically look very similar as well. You're always going to have a peak in the middle, as I said. This is the zero energy transfer. Across the bottom we have energy transfer omega, and over here we have a counts normalized in per microvolt bin. You have the quasi-elastic signal, which is peaked at omega equals 0, falls off as you go out in energy transfer, either energy gain or loss. In principle, you need to apply the equal partition of energy, but often your temperatures are such that that correction is minimal. And sometimes out at high energy transfers, you'll have real inelastic spectra, and you'll have peaks that might show up. The elastic peak, as I said, at omega equals 0. It's broadened by the energy resolution of the instrument. And often, one of the things that you're concerned with is how much intensity there is just in the elastic peak. You then have a broadened component, which may often be Lorentzian or a sum of Lorentzians, and we call that, typically, that's called a quasi-elastic scattering. And it has a width, and the width tells you how fast the motion is. So since energy transfer is the reciprocal variable to time, slow motions tend to appear very near the elastic peak. And so a slower motion will have a much narrower quasi-elastic component than a faster motion. Okay? Just like momentum transfer is the reciprocal variable to length. So large length scales mean small q's, and small length scales mean large q. So if you want to look at very, very slow motions, you need an instrument that has a very, very fine energy resolution. Okay. So the elastic peak will always be consist of the intensity that is truly elastic, or energy that is from processes that are so slow that the scattering is still within the instrument resolution. And this is part of the reason why the instruments that you use play a significant role in the types of information that you can get. An instrument with a finer resolution is able to measure slower motions. So we care about the intensity that's in the quasi-elastic peak and its breadth, and we care about the intensity that's in the elastic line. The ratio of the intensity in the elastic line to the total intensity is simply the elastic incoherent structure factor, and we'll talk about that later on. The connection in molecular dynamics is relatively straightforward. It's simplified because we're only going to talk about incoherent scattering. So we're going to talk about self-contributions, and we don't care about pair correlations. So all we have is a time-dependent correlation function given here. This is the intermediate scattering function. It's what it's often called. Sometimes it's shown in the literature as f of q and t or I of q and t, and it's got an incoherent subscript because this sum that you see over here on the right side of the equation is a sum only over individual atoms in your sample. It's not a sum over pairs of atoms. The things that show up in this formula are just the position, the atomic coordinate of atom I at some time t equals 0 when you start your calculation, and the coordinate at some time t later of the same atom I. And that's dotted in, those position vectors are then dotted into the q vector. And again, we often take a powder average, and so we average over all directions in our sample when we calculate our signal. So it's a very simple function. The only thing you need to calculate it are the trajectories of your atoms, and that's exactly what a molecular dynamics simulation will calculate. So you take the trajectories, the atomic trajectories, you weight the scattering strength by the cross-section of the atom, and sum over all the atoms in your system, and you have the intermediate scattering function. Its Fourier transform is just a dynamic structure factor, S of q and omega, which is simply related via phase space factor to the double differential scattering that you measure in the neutron scattering measurement. So the direction is relatively straightforward and simple, and all you need are the atomic trajectories. So if you look at a molecular dynamics simulation and the type of motions that you might be sensitive to, this is a cartoon of MCM41, which is a amorphous silica with well-defined pore volumes here in the middle. And this is one of the examples that we'll look at later on in this talk, chemically attached to some of the locations, some of the hydroxyl atoms have been displaced by doing the chemical attachment directly to the oxygen then of these molecules, which are essentially diphenylpropane. So there's a phenyl ring, a propane group, and another phenyl ring at the end. And the molecules are essentially free to explore the volume that's available to them, and they can pivot relatively freely about this base to which they're attached. So this is 1,3-diphenylpropane tethered to the pore surface of MCM41. And I'll show you now a molecular dynamics simulation movie. It's a little bit jittery, but it'll kind of illustrate the types of motions. As you watch the movie, I'll play it several times so you can kind of get an eye of what's going on. Take a look at especially what's happening to the whole molecule as it pivots and rotates through this space and as the phenyl rings rotate. Come up, and there it is. It's a little bit jittery because the time step's a little bit coarse, but you can take a look at the dynamics that's going on. The molecules tend to hang out with next to one another. They really don't like to traverse the vacuum that's the center of the pore. When they do traverse, they prefer to, for example, watch this guy. They'll move through the pore and then they'll try to find a place near a surface again. And that's kind of the tendency that we see in the simulation. And I think there's evidence in the quasi-elastic scattering that we measured from these types of samples for just this type of behavior. So we'll show this one more time. And again, keep an eye on this molecule. You're going to see the phenyl rings rotate. So that type of motion we see, and then the overall translational motion. In particular, in this case, of course, because the end of the molecule is pinned to the surface, you're not going to see any global translational diffusion. Overall, the molecule is constrained in space. Right? And that's going to give us a particular signature in the quasi-elastic scattering that we measure. We'll let this finish, and then we'll switch back to our talk. Okay, let's go on to the next slide. So those movies, of course, are created essentially from the atomic coordinates, the trajectories that would go into that equation. Let's see, there it goes. Those trajectories are essentially the values that go into this equation here. And so that's what you use to make the movie. So they're certainly accessible. There we go. Okay, let's talk about the elastic incoherent structure factor. The example I gave you has the atoms confined in a volume of space because they're chemically attached. If we took the temperature high enough, of course, we'd break that bond and the molecules would dissociate and diffuse through the pores. But in this case, they're not. So you can think of the elastic incoherent structure factor as a probability function. And it's essentially the probability that you're going to find the particle that you're interested in this case a hydrogen atom, at infinite time later, confined in the same volume that you start with when you started your clock. So that's kind of a difficult concept to grasp. And in particular, it has a difference depending on how good an energy resolution that you measure. So think of it this way. Let's draw a box around a hydrogen atom whose physical dimensions are just going to be given by 2 pi over the q at which we're going to make our measurement. Right? So it's a length scale. It's 2 pi over q. And we're going to start a clock, and we're going to look at some long time thereafter. The EISF essentially is the probability of finding that hydrogen atom, not another hydrogen atom, but that one, inside that box that we fixed in space, whose dimensions are 2 pi over q. So it's essentially, as I put here, the probability the particle can be found in the same volume of space at some subsequent time. When the particle diffuses out of this volume, okay, in a time that's faster then is set by the inverse of the resolution function of your instrument, you will measure quasi-elastic broadened spectra. Okay? And the elastic component in the middle is just going to be the probability that you find it back in that box. Right? So that's a little bit of a difficult concept, but you will see it used in the literature quite a bit, and so it's an important one to grasp. It is simply the ratio of the elastic intensity to the total intensity. So if this total intensity is properly normalized to 1, if it's a dynamic structure factor, then the elastic intensity is just the EISF, and it is just the probability that you'll find the particle back in the box at some infinite time later. So if you make this measurement with a very, very small q, then the box is very, very large. And if I made this box bigger than the size of the molecule that I have here in this simulation picture, then I'll always measure an EISF that's 1. I'll always measure all the intensity as if it were elastic, because the particle will never diffuse out of that box, no matter how long I wait, and no matter how good a resolution function I have in my instrument. And so you see that the EISF as a function of Q will decay from 1 at Q equals 0 to some other value that's determined by the probability that the particle will be in the box at higher Q. And that's determined by the geometry of the motion that you've got. And so if you predict a geometry, you calculate a model for that, you'll be able to determine what the EISF should be as you go out in Q. But it will start at 0, or start at 1 at Q equals 0, and then decay thereafter. Now, if the particle is actually free to diffuse, it's not tethered to this point, then the EISF will be 0. Because at infinite time, the particle will have moved away no matter how large a box you create. Right? So when you have particles that are undergoing restricted diffusion, one of the indications will be when you look at the EISF and you look at the Q equals EISF is tending to 1 at low Q, then the particle is undergoing some form of restricted diffusion. Maybe restricted to a volume or a surface or something else, but it is not freely diffusing anymore. All right, let's go on. That might be a good stop. If anybody has a question on the EISF and you want to type it in there, this might be a good opportunity. I'll pause for just a moment. Philip asks, how would you resolve the quasi-elastic part? I think. Was that Philip's question? No, that's your question. Okay. Sorry. Ming, there's another question. So how do you resolve the quasi-elastic component? The quasi-elastic component, let me grab the arrow again. A little bit awkward at this. It seems to disappear sometimes. So I can't get the arrow back. Well, that's interesting. Oh, there it is. Okay, now I've got it. The quasi-elastic part is the part that's differentiated, that's broader than the instrument resolution function. So the instrument resolution function will determine the minimum time scale or the the maximum time scale or the slowest motion that you're sensitive to in your experiment. So the quasi-elastic component arises when the hydrogen atom, in this case, moves out of our box faster than the maximum time scale that's set by the instrument resolution. So let's say we have a resolution function that's 100 microvolts, which is not atypical of quasi-elastic scattering. In that case, you're sensitive to motions essentially that are faster than, let's see, 100 microvolts, then maybe a few tens of a 10 or a few picoseconds. So if the hydrogen atom were to move out of that box on a time scale faster than a few picoseconds or maybe at 10 picoseconds, you would get a quasi-elastic component that you could resolve on the instrument that you were using. If not, then all the intensity is going to show up in the elastic component. And then, of course, if you make Q smaller and smaller, for a restricted diffusion, the probability that the particle moves out of that box gets higher and higher, and so the EISF will get smaller and smaller. So Philip asks or comments that then if the process is very slow, you should only see a delta function peak, and that is correct. You will see it, although broadened by the elastic resolution function of the instrument. Okay, from Penn State, if we calculate EISF as the ratio that I described, will you get a different EISF? Will the EISF you get for different instruments be different? You are absolutely correct. And we'll talk about that here in just a minute as we talk about the role that an instrument plays in the measurement that you do. So you will, even if you're looking at a single type of motion, the fact that different instruments have different resolution functions means that they're sensitive to that motion, say at different temperatures, where it may or may not be as broad as you're sensitive to. The other thing that you'll find in a quasi-elastic experiment is that you're also determined by how broad a range and energy transfer the instrument can sample. So if your instrument is unable to sample a broad enough range, then your quasi-elastic scattering will look essentially flat. It'll look like you're sitting at the peak of the Lorentzian, and all you'll see it is a very, very broad rise in what appears to be the background that you're measuring on your experiment. And so you need a combination often of instruments to probe the full range of dynamics that you might have present in your sample. One of the nice things, though, is that if you can tune temperature in your experiment, you can often control the width of the quasi-elastic scattering, and that gives you a nice way to move the scattering in and out of the window that your instrument is sensitive to. If you're on a chopper spectrometer, you may be able to actually change the instrument resolution as you proceed the experiment to keep it kind of in an optimal place to be sensitive to the motions that you're interested in. But yes, in principle, the EISF will depend on the instrument you measure, and that's why one needs to take some care in designing your experiment. I think that was all the questions we had. So let's go on. So let's talk about neutron scattering instruments now. As I said, QUENS probes diffusive motions. For typical quasi-elastic experiments, we're interested in Q ranges that might vary from about 1/10 of an inverse angstrom out to 4, maybe 5 inverse angstroms on some instruments. The Q range, of course, is set, the maximum Q is set by the wavelength that you're using in your experiment. It's just going to be 4 pi over the lambda. And so the length scale, of course, is the reciprocal of Q. And the lengths that we're typically sensitive to then are about 60 angstroms to an angstrom or two. The time scales, as I said, are set by the width of the instrument resolution function. Most quasi-elastic experiments are done with 100 microvolts of energy resolution or less, better resolution instruments. So higher resolution means you're sensitive to slower motions, longer time scales. The range of energy transfers that are typically available to quasi-elastic instruments are a couple of milli-electron volts or less. High resolution requirements emphasizes the use of cold neutrons, long wavelength neutrons. But the wavelength then limits the maximum Q that you're sensitive to. The incident neutron wavelengths that we use in quasi-elastic scattering typically range from about 4 angstroms to maybe as cold as 10 or 12 angstroms. 5 electron volts to about a milli-electron volt. So why do you see a wide variety of instruments? Well, that comes into how you design and build and optimize neutron scattering instruments. The resolutions might vary as much as 2 orders of magnitude, from 1 to 100 microelectron volts. When you design a neutron scattering instrument and you're designing it for high energy resolution, there's basically two terms that you have to understand really, really well. You have to know what the incident neutron energy is to some, basically as well or better as you want to understand the energy transfer. And you have to know what the final neutron energy is. And when you match that knowledge of the incident and scattered neutrons energies, you typically find that in order to get an improvement in the resolution of the instrument, you need to improve the resolution of both of those terms equally well. Okay? And that means that you add those contributions to your total energy transfer resolution in quadrature. So in order to improve the resolution by a factor of 2, you have to improve your knowledge of the incident energy of the neutron as well as its scattered energy. And so in order to improve a factor of 2, you have to improve the energy resolution a factor of 4. And the only way you do that on a well-optimized instrument is by throwing away flux. So in order to gain a factor of 2 on instrument resolution, you have to essentially pay a flux penalty of about a factor of 4. That paradigm is challenged in neutron spin echo techniques that you'll hear about, I believe, in your next lecture from Dieter Richter. But for these types of instruments, you're going to pay quadratically for improvements in resolution. So you can imagine if you have a very, very fast process that a 100 microvolt resolution instrument is sufficient for, you don't want to pay a factor of 10,000 penalty in your ability to make that measurement by using a 1 microvolt resolution instrument. So simply matching the resolution of the instrument to the time scale of the motion that you want to sample is going to make your experiment much more efficient and fast, and maybe be the difference between being a reasonable or an unreasonable experiment. So the choice of instrument depends then on matching the resolution that you need to the slowest time scale that you want to be sensitive to. All right. There are about 25 neutron scattering instruments in the world that can be used routinely for quasi-elastic scattering, and I'm including neutron spin echo as a high-resolution inelastic instrument there. There's a good number in the United States. The opportunity for doing these measurements is good. The competition for the beam time is high. NIST has a spin echo instrument and a chopper and backscattering instrument. The spallation neutron source has the same. They have different characteristics, but the same type of instruments are available. The trade-offs on selection of instrument are resolution and count rate, as we just talked about. A higher resolution instrument means that the count rate is typically down in quadrature to the resolution. The flexibility of the instrument. Backscattering instruments, crystal analyzer instruments, are typically relatively inflexible. You have your choice of Q and instrument resolution is determined by your initial selection of the analyzing crystal. And I'll talk about that here in just a moment. And then, of course, the neutron wavelength versus Q. Large wavelength neutrons make it much easier to come to the high energy resolution that you need so you can probe slower motions, but large wavelengths means that you have a very limited Q range. And so the short length scales that you might want to be sensitive to are just not accessible. Yes, ma'am. Okay. So let's go to the high-resolution neutron spectrometer landscape. This is essentially a phase-based map of neutron performance, instrument performance. Left and on the bottom are the variables we directly measured, the neutron energy transfer and the momentum transfer, and then the reciprocal variables on top and to the right, time scale and the length scales. And so let's go through. Backscattering crystal analyzer spectrometers cover a relatively wide range in this phase space, as shown by the blue area there. Chopper spectrometers, like cold neutron chopper at SNS or the disk chopper spectrometer, cover a somewhat broader range but are typically not able to reach the highest resolution, slowest motions that a backscattering spectrometer can. And then we have neutron spin echo, which uses a different way to encode neutron energy transfers, and they, on this particular phase space map, dominate because they are able to probe much slower motions at much larger length scales. So off to the right as I click through that are pictures of those types of instruments. The types of science that maps onto this phase space are molecules in confinement, like water on surfaces, or those molecules, those DPP molecules I showed you, confined to the pore volume of MCM41. Polymers and proteins cover a wide range of dynamics and length scales. Colloids and complex fluids, again, get weighted towards larger length scales and slower motions. And then small molecule diffusion, say lithium-ion battery, ions diffusing in electrolytes, or those types of things are, again, occur over a wide range of this space. Let's talk a little bit about instruments, and then we'll pause for a few more questions. Crystal analyzer backscattering spectrometers. In this case, one selects the neutron's final energy by allowing the neutrons that scatter from the sample to be analyzed or reflected by analyzer crystals, who are characterized by wavelength that they reflect back to the detector, and the variation in the d-spacing of the crystal. And so we typically try to keep the Bragg angle close to 90 degrees. That minimizes the contribution to the resolution function of the instrument. And so we'll either be in exact backscattering, which is typically how reactor-based instruments work, or close to backscattering, which is the geometry that's often preferred at pulse spallation sources. You can think of these analyzer crystals as energy selective mirrors. They take one energy out of the spectrum that's scattered by the sample and scatter it to the detector. So the detector always sees neutrons of the same final energy. In that case, in order to do energy transfer experiments, you have to sweep the wavelengths of neutrons that are in the incident beam. And they scatter then as the sample dictates, either elastically or up and down in energy, and only one neutron energy gets selected by the analyzers and hits the detector. So you use time of flight then. You start a clock when the neutron begins at a spallation source. You start that clock when the neutron begins at the moderator, and you stop it when the neutron is detected at the detector. Subtracting off the time it takes for the known final wavelength neutron to scatter from the sample to the detector gives you the time it takes the neutron to travel from the moderator to the sample. Since you know that distance, Li, you know its velocity, you know its energy, and the difference in those two energies is just the energy transfer that you want to use in your quasi-elastic experiment. So that is how backscattering instruments work. I've got a couple slides for a little more detail. The moderator pulse shape, this is how the neutrons come off the moderator in time. The units across the bottom are microseconds, and the half width, or the full width at half max of this is about 50 microseconds. Microsecond is essentially the natural time unit for measuring the velocity of a neutron, and that's what we use at this time of flight technique instruments. Okay. Oh, I forgot to tell you there's a reference to a paper here on how basis, the backscattering instrument at SNS works, and you can look that up later if you like. So how does the instrument work? We create these pulses. As they travel down the flight path, from any given pulse, the neutrons that are traveling faster get to a particular distance sooner than the cold neutrons from that pulse. And so the pulse stretches out in time and duration and length as you travel along the flight path. The neutrons then scatter from the sample, and they scatter as the sample dictates. And again, only a single wavelength or color of neutron is selected by the analyzer and directed to the detector. So time of flight selects the incident neutron velocity. The analyzer crystal tells you the final velocity, and the distance is just the energy transfer that we need for a quasi-elastic measurement. Things get a little more complicated though, because if the time between pulses is short enough, the fast neutrons from this pulse will catch up with the cold neutrons from the preceding pulse. And in that case, we won't know what the neutron's velocity was before it hit the sample. So we put choppers along the beamline to chunk up the spectrum that are produced by the source and the moderator. And we chop them into smaller pieces so that by the time the tail of the preceding pulse hits the sample and all the analysis happens and we measure it at the detector, the leading edge of the trailing pulse is just ready to hit the sample. And so that's how we truncate the pulses so we don't worry about what we call frame overlap. At an 84 meters, the distance of basis from the moderator to the sample, this band of wavelengths is about 0.7 angstroms. Direct geometry spectrometers choose to do their monochromatization of the neutron energy in a different way. We start with a pulse of neutrons and we may modify it along the path to the sample. But somewhere out here close to the sample, we put an energy selecting set of choppers. They move very fast through the neutron beam, and they're synchronized with the pulse of the neutrons that's generated at the beginning, so that the velocity of neutron that we want to choose is the one that's present at the location of this chopper when it's open. And typically these choppers will move through the neutron beam on order tens of microseconds to maybe 100 microseconds, creating a short burst of monochromatic neutrons, which then propagate to the sample. The sample scatters them, either elastically or gaining or losing energy, and then they travel to the detectors that are located at some known distance and geometry from the sample. In this case, each neutron travels with its velocity as dictated by the sample, and the time it takes for the neutron to go from the sample to the detector is the time of flight that we use to dictate or to know what the final neutron energy is. So we use the choppers in this case to select the incident energy and time of flight to know what the final energy is. These instruments are called direct geometry because they monochromate on the incident beam. And crystal analyzer spectrometers are called indirect geometry because they monochromate on the scattered beam. And so the instruments are kind of reciprocal with respect to one another. And in fact, the resolution functions are related by that symmetry. All right, that is where I'm going to pause for any questions that you might have to date. If you have any questions about the concepts of QENS, the roles of the instruments, or how the instruments work, now's the time to ask them. When we finish this, we'll go on to a couple of examples of the types of science that you can do and the information that you can get. These are examples that are published, and so you can go and look up the papers later on. And there are two examples. One where the molecules are tethered, as they were in that MD simulation, and the other where the molecules are free to move in solution. And so we'll kind of go through both of those and the types of information that we can get. Okay, what is the monochromatic range? I'm not quite sure what you're asking there. Do you want to know how monochromatic the beam is? That is, its wavelength resolution? If you do, the wavelength resolution that the time of flight gives us for the backscattering spectrometer, say basis, is about 3 parts in 10,000. So the monochromatization for very, very high resolution instruments is on that order, 1 to a few parts in 10,000. So by stretching the neutron pulse delivered by the moderator over 84 meters, basis knows the velocity to about 3 parts in 10,000. On a chopper spectrometer, the natural unit to use is now back to energy. And so one might often use, say, a 2 milli-electron volt incident neutron, and you might set the chopper velocities up so fast fast enough that you know its energy, the energy is monochromatized to maybe, I'll say, let's see, so for 2 millivolts, maybe about 40 to 50 microvolts. That's about where you'd like to be, maybe 60. And you can make that, you can broaden that, get more neutrons, and maybe you're out to 100 microvolts or so. Okay, Penn State, is the volume element a sphere or a cube like you've drawn it? And I think there you're probably talking about the cube that I drew for the EISF. In principle, it's essentially, it's an XYZ volume element. So I think that may be asking a little bit too much from that intuitive look I gave you, but for me, the coordinate system in that case would be Cartesian, so an XYZ volume element. Okay. Okay. Did I have any more questions there? All right, well, let's move on then to a couple of examples. And we're going to go back to my example of diphenylpropane molecules tethered to the surface of MCM41. So in this case, the center of mass of the molecule cannot diffuse because the end of the molecule is pinned to the surface. And here's a little bit more of a schematic cartoon of how the actual chemical attachment happens. You've got an oxygen that used to be the oxygen of a hydroxyl. The chemistry happens by replacing the hydroxyl, doing a little bit of chemistry on this end of the molecule. Here we have a phenyl ring, another phenyl ring, a propane linker between the two, and then we've got hydrogen atoms decorating all along the length of this molecule. And because they're hydrogen atoms, they're going to dominate the scattering that we're going to measure in our experiments. So some of the particulars, in this case, we looked at pore diameters that range from about 1.6 to 3 nanometers. And I'll warn you later on that sometimes I switched back and forth from nanometers to angstroms and forgot to move the decimal point. So sometimes I called it 16 nanometers. That should really be 1.6 nanometers. And we could control how many DPP molecules we attached to the surface. And we could control the temperature at which we made the measurements. So those are the experimental parameters that we're going to explore in this particular experiment. And remember, because the molecules are tethered and restricted in space, there is an EISF. So the scattering that we measure at very, very low Qs should tend to 1 and all be elastic. All right. One of the things that you can do at a reactor-based backscattering spectrometer is you can stop the monochromating device, which is often a Doppler-driven crystal monochromator, and you're using Doppler shift to move the incident energy around. You can stop it and put all of your energy, all of your intensity into the intensity that is only at the elastic line. And so you can make very, very rapid measurements of the elastic intensities on these instruments. And so this is often a great place to start your experiment, particularly if you don't know where the quasi-elastic scattering is going to come up. So I've got two what we call elastic or fixed window scans that were done on the high flux backscattering spectrometer at NIST. One where we looked at the number of DPP molecules that were attached to a relatively large pore, and over here where we changed the pore sizes and we attached as many molecules as we could to the surface. And so the intensities are not normalized to one another, but let's start over here. At highest pore coverage, at highest coverage of DPP molecules, we of course had more hydrogen molecules, and so we had more integrated intensity. In this case, we're integrating all the intensity in all the detectors, so over the entire Q range of the instrument. And as you go down in coverage, your total intensity changes. You can see that the intensity tends to fall off relatively linearly with temperature, with increasing temperature, until you get to some temperature at which you start seeing curvature. And that temperature actually is where you are starting to get intensity from your sample that is showing up in the dynamic range in the within the resolution of the instrument. So the intensity is moving out of the elastic peak and into the quasi-elastic range. Down here is the intensity that I've got from the initial MCM41 substrate to which I've attached everything. So you can again see that the total scattering that I measure is really dominated by the hydrogen atoms on the molecules that have been attached. Over here at the pore size dependence, you can see somewhat similar behavior, although you can see that the curvatures are changing a little bit. You can take another step beyond just looking at the integrated intensity and figuring out where your dynamic transition is beginning to show up by analyzing the intensity as a function of the Q that you're using. So now you can take a harmonic approximation and say that the intensity should fall off with simply the vibrational amplitude of the motion. And in 3 dimensions, it falls off with Q as e to the minus Q squared U squared over 3. And now I'm going to take the intensity at each detector, at each Q, and model it by this equation and extract the the ensemble average vibrational amplitude. Okay. And if I do that and I plot that intensity now, the vibrational amplitude as a function of T, I see that at low temperatures there's essentially a linear response, and then at some critical temperature the intensity starts to deviate from that. That temperature is just the temperature at which you are sensitive to the onset of diffusive and anharmonic motions, at which this equation is not able to capture. And so this is, in proteins, this has been identified as something you'll see in the literature as a dynamic transition, happens around 220 degrees for hydrated proteins. But it's just the temperature at which the dynamics starts to move into the range that your instrument is sensitive to. The other thing you can do is model the low temperature slope, its increase with temperature. So if you have a potential that's harmonic and it is very deep, okay, then it's going to your system is going to go to higher and higher temperatures before you start moving your atoms far enough up in that potential well to either experience its anharmonicity or to diffuse out of that well and see diffusive motions. So this transition temperature essentially is a measure of the depth of the potential well that your atoms are sitting in. The slope is essentially a measure of its breadth. So if you have a very, very broad potential, then then it doesn't take much temperature for the amplitude of the motion to increase a lot. And that's what you're seeing here with the slope. So that's a way to think about these types of measurements. These are used a very large amount over the last decade because these types of measurements are extremely fast. You can combine information from all your detectors for these types of scans, and these types of scans are very readily analyzed almost instantly. The time it takes to make a single temperature measurement for a reasonable sample in this kind of experiment can be as low as a few minutes. So it's very good for doing survey experiments and understanding what temperatures your dynamics is occurring over, and even getting some particular information like these two for parametric studies. So in the interest of time, I'll just let you look at this slide later. Just summarize some of the observations that I've made from that previous graph. Essentially, there's no dependence on the surface coverage. When you do vary the pores, there was something magical about this 2.1 nanometer pore. And if you look at these snapshots from the MD simulations, what you find is that at very small pore sizes, the molecules cannot adopt a conformation which allows them to get uniformly close to the surface, and they're forced into the pore center. At very, very high, very large pores, the molecules are far enough apart from one another that they can actually adopt conformations which allow them to stay close to the surface. And of course, they don't want to be out in the middle of the pore unless they can be next to another molecule. That doesn't happen in the large pores, but it does happen ideally in this kind of intermediate range pore size. So this is the pore size at which the molecules can kind of sit in the deepest harmonic potential, when that is what drives up this dynamic transition temperature, as you saw in the previous slide. So let's take now a look through some of the very simple types of fits that one can do. In this case, we're going to just fit the quasi-elastic spectra, which looks like this. This is the resolution function of the instrument. And we're going to fit it to a delta function convoluted with the resolution function, and a single Lorentzian, also, of course, convoluted with the resolution function. And so we get the elastic intensity, we get the intensity in the Lorentzian quasi-elastic broadened component, and we're going to take the ratio and get the EISF. So this is now a little bit more of a model of the data, and let's see what we can learn when we have the EISF. Here is the EISF now for a 30 angstrom pore size with maximized DPP coverage. And you can see the model I've used is one of restricted diffusion. So the solid curves are a model of restricted diffusion, and the circles are the results from the experimental measurements using the curve fit, the fitting model that I showed before. It's very difficult in these cases to get to small Q's, although I'd have loved to, and that's because these pores were giving rise to very large small angle scattering contribution, which in my case was background, and something that was very difficult to deal with. So I measure from about Q of 0.5 out to the maximum Q of the instrument, which is about 1.7 or 1.8 inverse angstroms. You can see at low temperatures, the EISF does tend to go up here to 1 at Q equals 0. It does fall off a little bit with Q as you go out in Q. At all temperatures, it asymptotes to a finite value of Q. This zero asymptote implies that at all three of these temperatures, there are hydrogen atoms in my system which are immobile on the time scale of my particular experiment. For this instrument, that was around 2 or 3 nanoseconds. Okay, so at 2 or 3 nanoseconds, even at 320 degrees Kelvin, there are hydrogen atoms that can't move. And in fact, the fraction of hydrogen atoms that can't move is just this value, this asymptoted value. So about 60% or so at 320 degrees. This curvature, as you approach Q equals 0 and 1 for the EISF, determines the maximum pore radius, or the maximum spherical radius at which the atoms can diffuse through. And I'll show you the model for that coming up here in a minute. So the EISF can be very informative in terms of the types of motion, the geometry that we can see in our sample. It tells us the maximum size and length scale of the motion, and it tells us, in this case, that some of the atoms aren't diffusing at all. There's a population left that are immobile. If I plot the Lorentzian half-width that I get from that model, and I plot it now as a function of Q squared, I find that it goes to a non-zero intercept. That is another indication and a hallmark of the fact that the motion is restricted. Restricted diffusion will always asymptote in to some non-zero value of gamma at Q equals 0. Let's move a little bit beyond the very simple model now. And we'll introduce something that's a little more complicated, but still not bad. This is a model of diffusion in a sphere that's fixed in space with impermeable boundaries. So you think of the hydrogen atom as able to freely explore the volume of this sphere. It has a radius r, okay, and the hydrogen atom has a diffusion coefficient d. You can look these coefficients up. They're worked out numerically. We're going to do a sum over some value, number of L's and N's. Typically, you don't need very many, 9 or 10 of those, before this sum converges. And so we have a diffusion coefficient, a radius, And we have over here an EISF, which depends only on the radius and the Q. Okay? And we've got it right here. It's just a simple Bessel function. And again, the model is here if you want to look it up. This is one of the simplest cases, and it's used quite broadly in the literature for motion that's restricted in space. All right. Now, let's go back to our cartoon of the attached molecule. You can see that we've got hydrogen atoms that are attached at a lot of distances for an extended molecule. And it should be somewhat intuitive to you that molecules that are close to the attachment point are unable to explore a sphere as large as the molecules that are farthest away from the attachment point. So we're going to put in a diffusion model for each one of these hydrogen atoms that has its own maximum radius that's determined by how far that atom is from the tether point. Okay? And we're going to give it a diffusion coefficient which depends on that radius. And that's kind of the model that we're going to use. It's given here as it's in its entirety. We're going to leave a component of elastic scattering that's from the MCM41. We're going to measure that independently. We're going to have an elastic contribution from the DPP molecules, which is going to reflect the fraction of molecules that aren't moving. And then we're going to have a fraction of the molecules that are moving, the hydrogen atoms that are moving. And that's going to multiply our diffusion in the sphere model. Right? So the mobile fraction are just the ratio of this to C0, to C1 plus C2. And we're going to fit all of this simultaneously to our spectra at all Q. And if we do that, you can see that we get very nice fits. This is now a basis data set. You see the elastic scattering, the quasi-elastic broaden. This is a logarithmic scale. This is over a very large dynamic range. And this is as a function of Q. And you can see that that model fits the data very, very well. Now we can extract a lot of information from that model. We can look now in more detail at how extended is the motion. And we've got that plot right here. You can see that kind of counterintuitively, the radius of motion decreases as one increases the size of the pore. And the reason for that basically is that in small pores, the molecules are forced away from the surface, and so they have to explore the volume of the pore itself. As you go up in coverage, for a given size pore, the pore volume also tends to increase. And again, that's because in both those cases, the DPP molecules are forced away from the surface of the MCM41 and into the pore volume where there is more space for them to actually diffuse. You can look at how fast the motion is, and I'll leave that to you here in a moment. This is one point that I did want to address because it came up. What happens when I measure the same system on two very different instruments? Both of these are backscattering instruments. The two samples are very similar. The backscattering instrument here has a much higher resolution, 1 microvolt, but only has a dynamic range of about plus or minus 18 microvolts. The basis over here had 3 microvolts, a poorer resolution, but a much broader dynamic range. And what you can see is the dynamic range on HFBS was not broad enough to watch the Lorentzian, the broadened quasi-elastic component, decay to 0. And that has implications on the effective breadth that you measure when you actually model this data. Whereas basis was able to measure it over a very, very large range of energy transfers and essentially watch the Lorentzian decay much closer to 0 or to the background level. This data, by the way, is also published in JPhys Chem C, and you can look it up. The two instruments give you then different diffusion coefficients. The interesting thing is, though, that the activation energy you calculate, even for the two different resolutions and the two different absolute values of the diffusion coefficient, are very similar to one another and almost identical within the error bars. And so that's a very interesting observation for this particular instrument. The geometries of the motion that you determine and the fraction of mobile molecules that you determine, however, are very, very similar and follow the same trends for both instruments. And that's because these two parameters essentially depend on measuring the elastic intensity very well. And both instruments are able to measure the elastic intensity well, regardless of the dynamic range that they're sensitive to. So you can take a look at the second example. This is one of dendrimers, and they have a wide range of usefulness across medicine in particular. And let's go to another slide. We're going to look at this system now, about 50 milligrams of protonated dendrimer dissolved in 1 milliliter of deuterated solvent, primarily D2O. As you charge the arms of this dendrimer, you can change the conformations such that at low pH to neutral, or sorry, high pH basic conditions, through to low pH, you change the density distribution of mass in the system from a dense core, a compact core, to all the way out to a dense shell, where you see the arms distributing out to the edge. This is what a small angle scattering experiment tended to indicate. And if I go on now to a quasi-elastic experiment, I'm going to use my same model for the local diffusion of the arms, but now I have to account also for the fact that the center of mass can diffuse in the solvent. It's no longer just a powder. And so now I've got two contributions: the internal motion of the dendrimer arms convoluted with the center of mass motion of the dendrimer as a whole in the solvent. We chose to measure that center of mass with an NMR technique so that we could limit the parameter space that we were fitting our data with. So that's the shaded region. And if we take that then as the value for the center of mass motion, which extended out here to energy transfers, as you can see, to about 40 micro electron volts, you can then model the rest of the scattering by the internal motion of the dendrimer arms. And interestingly enough, as you charged the dendrimer arms, you might have expected them to become a little more stiff. And instead, this broadened, charging the arms broadens the quasi-elastic spectrum. And in fact, the motion of the internal motion of the arms gets faster and faster as you protonate. In fact, they get about twice as fast when you're fully charged as they were when they were in the uncharged state. There's a couple of reasons that can happen. One might be crowding of the arms themselves as you go from a dense core to a dense shell. The other is the nature of the water that's associated with those now charged amine arms. And you can see one paper on that, again, published in Soft Matter. So we're going to finish with my reference materials. These are some of the books that you might be able to find in your library. This one we mentioned earlier. I know it's in print. This one I believe is still in print. This one you would have to find out of print. And this wonderful book by Mark Bay is out of print. But if you can find a copy of it, you should really take a look, because it is a textbook on quasi-elastic neutron scattering. Some other papers that are classics in the field: Van Hove, that relates classical distribution functions to the quantum mechanics that you're actually measuring in a scattering experiment. These are wonderful. Barley Sears had a nice series of papers talking about restricted motions on the surface of a sphere. This paper by Vineyard is also a classic, and this article by Chandrasekhar really looks at a variety of types of diffusion, whether it is a diffusion of a density or single particle or fluctuations otherwise, and I'd recommend it. Data analysis: there is a software suite that was developed by the NIST Center for Neutron Research called DAVE, and it gives you some fundamental tools to look at your data. So I'd highly recommend any of those. And in summary, you can take a look at this slide, but these are some of the things that I find most valuable about quasi-elastic scattering. So if you have any questions, I'd be happy to try to answer them. I think we have maybe a couple of minutes. So I'd like to thank you for your attention up till now. But if you have any questions, now's the time. So the question from the audience here was, if I'm taking this model, how do I know that I only need a single Lorentzian? Yeah. And what's my criteria for choosing that, and also for deciding that this is an adequate fit? And typically what we know, there's elastic scattering. Okay, so I know I need a delta function because I can see it. This is a logarithmic scale, so you can see. And then what I would do is I would start, if I don't know anything else about the geometry of the motion, and I can't pick a more complicated analytic model, I would start with a single Lorentzian. And if that single Lorentzian combined with the delta function are sufficient to give me an adequate fit, so you can pick something that's got a chi-square from the fit, a reduced chi-square, near 1, then sure, I can throw more Lorentzians into it, but I'm just fooling myself if I think that I'm getting any additional information out of that model. Now, if a single Lorentzian goes in and I can see that I've got some systematic residuals left that also show a broadened component, then obviously a single Lorentzian is not enough. And I may need either an additional Lorentzian or a distribution of Lorentzians or some other line shape in order to capture those intensities. Often, though, a single Lorentzian, if you only have a single dynamical process that decays exponentially in time, then a Lorentzian will capture that intensity, and it's very often is enough. But if you have more than a single process happening, like two different populations of atoms or in your system, and they're doing two different types of motion, then you might need two Lorentzians. One of the nice things is, though, is that if you can tune your temperature, you can often move them to areas where maybe one is dominating over the other. So I would simply look at the quality of my fits and make a judgment call on whether or not I've captured all of the information that I'm going to get out of the experiment.
Actually, chi-square is not the only criteria for us to say if our fit is good or not.
True, you can go to more. The comment was that chi-square may not be the only convergence criteria that you want to consider, and you can use other more sophisticated tests. It's just that a lot of the programs that you have available do a typical linear least squares fit. Chi-square is the variable that often comes out most readily. So it's about the easiest way to do it.
Thank you.
You're welcome. Another question in the audience. Right. So the question from the audience was, why can't you actually go ahead and determine those diffusion coefficients better, even if it's the same motion, maybe even the same sample? Why can't you? What is actually limiting you to measuring a smaller diffusion coefficient on an instrument with a higher resolution but a smaller range? So let me go to that slide and I'll try to explain it a little bit. And the bottom line is statistics. So here's the slide that compares the data from the two different instruments. The one on the left with the higher resolution but the smaller dynamic range, and the one on the right with the somewhat poorer resolution but much broader dynamic range. And as you can see, the problem is also the fact that you've got a Lorentzian line shape. Lorentzian line shapes decay very, very slowly to 0. And so if you don't have enough dynamic range to actually measure it to 0, I could have probably fit that. This is pretty decent statistics data, to be honest. And the Lorentzian itself, in this case, is pretty well sampled in this range of the data. But if I had even noisier data, this Lorentzian could have been, half the width, and I would simply be modeling a background that was higher. So it really comes down to the fact that in quasi-elastic scattering, you're measuring a line shape that decays very, very slowly. And if you don't measure it with enough statistics, it's going to be ill-determined what its width is.
So why doesn't that emerge in the error bars? Because you're making two choices, the Lorentzian and the background.
Yes, you are. And it does. So It would show up in the error bar in the width, yeah, because you've got a stronger correlation between those two nominally, which you'd hope would be independent variables. So I think it really comes down to the fact that you've got a line shape that decays slowly, and you want to make your measurement in a finite amount of time. All right. Any other questions that somebody might have? Another question in the audience.
Okay.
Yes.
So generally speaking, so for the translation motion, it's following the Lorentz function. But how about the rotation and the vibration?
So vibrations, remember, so the question is, if translational motion is in the quasi-elastic, what about rotations and what about vibrations?
Exactly. Yeah.
So within the quasi-elastic approximation, vibrational motions, per vibrational motions, show up as flat. Okay? And they take intensity from the elastic peak, redistributed over a large range of energy transfers, but still near zero. So it looks almost like a flat background. Okay? So that's with the vibrational, and that's when I was simply doing the fixed window elastic scans, the low temperature, that's all I was seeing was the vibrational motion. Right? As you go up in temperature and you see the restricted, say, a rotational diffusion, when that starts to turn into, and the crossover between very, very large amplitude harmonic and librational motion and true rotational motion is kind of a soft thing. Okay, so you'll start to see quasi-elastic scattering though for large amplitude librational motions and for true rotational diffusion. You'll see that in the quasi-elastic broad Lorentzian component.
So actually we can indeed see that the intensity of the vibration and the rotation should be very, very low, right? It's close.
So the vibrational intensity will still be there, but it'll appear nearly flat across your energy transfer range. So it'll look like your background is going up, like you have a temperature-dependent background, as your elastic peak goes down. So that's what vibrational looks like. You're welcome. All right. I thank you all for listening, and I hope you go out and try quasi-elastic scattering if it can answer a question.